Our next speaker is Konstantinos. He's at ETH, and he's going to speak to us about Virtuoso, enabling fast and accurate virtual memory research via imitation-based operating system simulation methodology.
Hi, everyone. I'm Konstantinos. Thanks for the introduction. I'm excited to present to you Virtuoso, enabling fast and accurate virtual memory research with an imitation-based operating system methodology. It was a collaborative work between Safari, TH Zurich, and other institutions. So let's jump to the important stuff. So we have GPUs, CPUs, smart NICs, and other devices nowadays, which are all using virtual memory. So this renders virtual memory a cornerstone of modern computing systems. And the big question is, does virtual memory come for free? As many of you know, it doesn't come for free. It causes high performance overheads because of two key reasons. Memory allocation, we spend time in allocating memory, and others translation. We need to translate virtual to physical addresses. So let's jump to the memory allocation overheads first. So we have emerging workloads like function as a service, serverless computing workloads, and some short input, short output, large language model inference workloads that have two properties. They're short running. They might run, for example, for less than a second. And second, they have a high spawning throughput. So what happens in these workloads? So we spend a lot of time in the operating system for memory allocation routines, while the actual execution of the workload is short. And the time we spend in the operating system cannot be amortized due to their short execution. So in this plot, we demonstrate the fraction of the total execution time of the physical allocation, of physical memory allocation across diverse short-running workloads. And we observed that on average, 32% of the execution time, which we measured in a real high-end server-grade CPU, is spent on physical memory allocation. So let's jump now to the address translation overheads. We have, again, another class of emerging workloads. Sparse machine learning like GNNs, bioinformatics workloads with vast data footprints, graph analytics, databases, which might be much more long-running, more than 100 seconds. And they also exhibit irregular memory accesses. And in these workloads, we have lots of TLB misses that leads to page table walks, and these constitute a high address translation latency, which does not allow us to fetch the data quickly. In this plot, we demonstrate the fraction of the total execution time spent in address translation for 9 irregular workloads, 9 random workloads. And on average, 26% of the execution time, which again we measured in a real system, is spent on address translation. So putting everything together, address translation causes high overheads in diverse emerging workloads, in both short-running and long-running workloads. And these overheads of virtual memory are expected to increase as we transition to larger physical address spaces. Going into the future, we already have unified memory with GPU and a CPU memory. We will have direct storage access using a byte addressable interface to access a high-end SSD. And we also have memory disaggregation, so we could access both remote devices and local memory modules. And researchers try to save the day. How? By co-designing the hardware and the operating system to reduce these virtual memory overheads. For example, they employ software-managed TLBs to achieve this. Another class of works tries to leverage virtual address to physical address contiguity to achieve this. Another class of works try to accelerate memory allocation. They throw specialized hardware for memory allocation to achieve this. Another class of works try to use alternative address mappings, like hash-based mappings, to accelerate address translation. And there are many more we cite in the paper, which try to co-design hardware and the OS, like rethinking the page table design, employing multiple page sizes, and many more. And putting everything together, we have a wide range of hardware OS co-design techniques that aim to improve virtual memory. And if we want to effectively evaluate these virtual memory techniques, this would be very crucial for the progress in the domain. But there are some challenges in the evaluation. Why? Because there is a very frequent interplay between system components when it comes to address translation. The software level memory management, which is the OS, the hardware memory management unit, and other system components like the DRAM or the shared last level cache. An example, we have the page table whose size depends on the OS allocation policy. So when the OS can provide plenty of large pages, then we can keep the page table small. We do not need as many entries. But once fragmentation starts rising, we cannot allocate many 2-megabyte pages. In this scenario, the page table becomes much bigger. And when we have a very big page table, we need to access many page table entries, we might cause interference between actual data and page table data in the main memory. So in this figure, you see a DRAM bank with many rows, and the row buffer, which is a hardware structure that stores the most recently accessed row. And in this example, we have two applications, application 1 and 2, and one of it is storing page table entries, the other one is storing program data. In this scenario, when we want to access the page table entries of application 1, we need to cause a conflict in the row buffer, reload it, activate it again, and bring in the page table entries. Next time application 2 needs to access its program data, it will cause another conflict, which means that application 2 will be slowed down because of this conflict. The page table accesses, these frequent accesses, do not cause only high interference between the application itself, but it can cause high interference between this application that is causing it and other applications that are co-running in the system. So evaluating the interplay between the components is critical when we want to assess current and new virtual memory techniques. And researchers have architectural simulators at their disposal to achieve this. So existing simulators, there are split into two classes, basically, emulation-based and full system-based. In emulation-based simulators like Ramulator, Sniper, ChampSim, and ZSim, we have very high simulation speed where we focus on a small subset of microarchitectural features. However, we have limited support for operating system primitives, and they typically use analytical models to estimate virtual memory overheads. An example is that they use first-order models to estimate these overheads, which you think of them as simple mathematical or algorithmic approximations. For example, we set the page fault latency and the page table walk latency to static numbers. And the question is this good enough? And in this plot, we demonstrate the average page table walk latency in 53 benchmarks with varying memory intensity levels measured in a real system. And we observe that the average page table walk latency can range from 33 cycles up to 184 cycles, which means that we have a very high variability into the page table walk latency. We cannot set a static fixed number for it. And in this experiment, we measured the memory allocation latency using ftrace with THP disabled, transparent huge pages disabled, and enabled. And as we see, the contribution of the outlier values when we enable THP, which means above the 75th percentile, is 67% of the total latency. However, when we disable THP, the outliers only contribute to 25% of the total latency, which means that the latency of handling the memory allocation, again measured in a real system, exhibits very high variability. So the first-order models cannot accurately capture the dynamic nature of virtual memory overheads. So that's why full system simulators are there for us. We have Gen5 full system, QFlex, PTL-Sim, and more. And these enable the execution of a full-blown OS on top of a hardware simulator. But they have low simulation speed, and they're hard to develop. They have a buy-in time which is very high, especially for young students, for example. So these two classes of simulators create dichotomy. We have simulators with much higher simulation speed but lower accuracy, and some others with much lower speed but much higher accuracy. And in this work, our goal is to bridge this dichotomy and have simulation infrastructure that is both fast and at the same time can model with high accuracy the virtual memory overheads. To enable fast and accurate virtual memory research, we propose Virtuoso, a new simulation framework that enables fast and accurate prototyping and evaluation of the software and the hardware components of virtual memory. At the core of Virtuoso is an imitation-based simulation methodology. So we use a lightweight user space kernel written in a high-level programming language, where we choose only the OS modules related to our desired research. And it tries to imitate the full-blown operating system. An example, we have the full-blown operating system with many modules like managing NUMA, protection bits, C groups, and we choose only some of them related to our research. And that's how we came up with the lightweight user space kernel that has only 3 modules in this example. This enables rapid development and prototyping. We also have high simulation speed by executing only the desired OS kernel functionality. And we have accurate evaluation by integrating Virtuoso with our desired architectural simulator. So let's get an overview of how this works. We have our lightweight user space kernel, and we have a simulator running below it. We instrument the instructions of the user space kernel when it needs to serve a request, and we stream them to the core model using an instruction stream channel. So once we start streaming them, and then this operation finishes, we can evaluate and imitate the operating system level overheads caused by the user space kernel. When this process finishes, we deliver the functional outcome to the simulator, for example, our allocated page size or our allocated page, and this enables also the emulation of the kernel modules. Let's dive deeper into a detailed example of a page fault handler that uses only two modules, the transparent huge page allocator and the body allocator. Again, we have an example simulator, the sniper simulator, and we run at the same time that we spawn the user space kernel and our workload. So when the workload sends a memory access to the core model, the core model sends a translation request to the MMU model, the memory management unit model, which triggers a page fault. We could not find the page table entry. The page fault handler gets invoked at user space, and the binary instrumentation tool generates a stream of instructions back to the core model as a feedback, so that the core model can aggregate in total to the translation latency, the latency of the page fault. When this process finishes, the page fault handler communicates the page fault outcome to the simulator. We built MimicOS, a lightweight user space kernel that mimics the Linux kernel with many modules written in C++. You can find more about how MimicOS works in the paper. Building on top of MimicOS, we built Virtual, a state-of-the-art virtual memory technique. So we built a tool set that encompasses the hardware, both the hardware and the software components of multiple state-of-the-art virtual memory techniques, different page table designs, software-managed TLBs, and much more. We believe that Virtual can enable researchers to evaluate and prototype current and brand new virtual memory techniques, which renders Virtuoso a highly versatile simulation framework. We integrate Virtuoso with 5 diverse architectural simulators like Gen5, System Call Emulation Mode, Ramulator, Sniper, ChampSim, and MQSim, so that we enable studies where you need to interact with the storage device. We validated Virtuoso against a real system. We ported it on top of Sniper, and we validated against a Linux kernel running on top of a high-end server-grade CPU. And in this plot, we demonstrate the IPC modeling accuracy in the y-axis for 3 configurations: the baseline Sniper, Virtuoso plus Sniper, and the best performing simulator, which was Gen5 full system. And we make 2 key observations. First, when we integrate Virtuoso on top of Sniper, we can improve the IPC modeling accuracy by 21% compared to the baseline Sniper. Second, Virtuoso integrated with Sniper achieves an IPC modeling accuracy within 9% of Gen5 full system simulation. We also measured the page fault modeling accuracy achieved by Virtuoso, ported on top of Sniper. And what we observe here is that Virtuoso integrated with Sniper models the page fault handling latency with 66% accuracy within 15% of the Gen5 full system, which means that there's more work to be done here to bring it much closer to Gen5 in the real system. We also measured the simulation speed of Virtuoso and MimicOS ported on top of different simulators, ChampSim, Sniper, Emulator, and Gen5. And we observed that MimicOS leads to an average 20% simulation time overhead over the baseline version of the simulator. However, when we enable the full system execution mode in Gen5, we get back a 77% simulation time overhead, which makes Virtuoso and MimicOS another alternative in the accuracy and speed trade-off. We showcase in this work Virtuoso's versatility by evaluating multiple different use cases, where we try to demonstrate new insights on state-of-the-art virtual memory techniques. We have 5 use cases in the paper described in detail. In this talk, I'm going to describe 2 of them: how we can evaluate different page table designs and how we can evaluate different physical memory allocation policies. Let's jump to the page table designs. We have 2 designs: the simple radix-based page table and elastic cuckoo hashing, which is a work published by Dimitrios Karlatos in ASPLOS'2020. We also sweep the fragmentation, which means how many 2 megabyte pages we're providing to the application, and we tested it on multiple workloads with irregular memory accesses. In this plot, we demonstrate the reduction in the total page table walk latency over radix achieved by elastic hashing over radix. And what you observe is the following. As we decrease memory fragmentation, which means we provide more and more 2 megabyte pages, the page table walk latency reduction of elastic hashing compared to radix increases, which means that the more 2 megabyte pages I provide to the elastic hash table, the better I perform in terms of translation latency. But when we have a very high fragmentation, let's say 100%, elastic hashing needs to perform many accesses to the main memory, much more than radix. So in this plot, we demonstrate the normalized DRAM row buffer conflicts of elastic hashing compared to radix. And we see that elastic hashing leads to an average 52% increase in DRAM row buffer conflicts over radix. Second, let's go to the physical memory allocation policies. We evaluated two designs, the baseline allocator that uses a very simple allocator, only the body system, nothing else, and Utopia, a work we published in Micro 2023, where part of the memory, a smaller part of the memory, is organized using a hash-based virtual to physical mapping. And for workloads, I'm using our favorite sort input, sort output LLM inference from Mistral, Llama, and Bagel. And in this plot, we demonstrate the physical memory allocation speedup for a Utopia configuration where we have a segment where we can map 32 megabytes of data in a hash-based manner. And we observe that restricting the virtual to physical mapping speeds up memory allocation by up to 2.17x in these sort input, sort output inference workloads. There are many more details in the paper about how we can integrate with different simulators and with respect to different use cases. And you can find the definitive version on archive where you can find the latest updates on the paper. Virtuoso is open source. You can find it on GitHub. We have a website where we have some preliminary documentation. And there's also a release notes with when the new features arrive and which features we have already released. In conclusion, virtual memory causes high overheads in emerging workloads. We introduced Virtuoso, a new simulation framework to enable fast and accurate virtual memory research. Our imitation-based simulation methodology leads to rapid development and versatility, high simulation speed, and accurate simulation. We integrated Virtuoso with 5 simulators. We introduced Virtul, a toolset encompassing multiple state-of-the-art virtual memory techniques that enable researchers to do great virtual memory research. We validated it against a high-end server-grade CPU, and we implemented 5 diverse use cases to show Virtuoso's versatility. And you can find it open source on GitHub. And we hope finally that Virtuoso establishes a common ground for virtual memory research. Thanks a lot, and I'm happy to answer questions.
This looks like a nice advance in simulation technology, and I appreciate it. I just have to be that guy and say the Champ-Sim for a while has had a realistic page table walker in it, and I just want to make sure that that didn't kind of come through in the talk. I want to make sure that.
Yes.
Thank you.
Yes, Champ-Sim, I confirm, has a realistic page table walker. How Virtuoso would enhance Champ-Sim is by providing basically, for example, an allocator so that the page table walker knows which pages are 4 kilobytes and 2 megabytes, and what would be the overheads of this allocator when we run a program.
Hi, Kanellopoulos, great talk, great work. You showed a few figures where the accuracy of all sorts of 5 and some of the tools are actually quite high. Do you have any insights of what's going on and like how we're going to close this gap?
You mean the accuracy drop is high? Yes. So I think this accuracy drops comes from many. It has come from many components. In these workloads where we saw the other translation problems, the accuracy mainly comes from what we've seen from the main memory model. So we have many requests coming to memory, and if your main memory model is not good, then it doesn't matter basically what you do with the other models. And another thing that you may not be able to capture with these simulators, I think this is the case for Gen 5 full system as well, it's not easy to capture the overheads of, for example, the context switches. What exactly happens in the context switch? But it heavily depends on the workloads as well. Yes, in these short-running workloads, we observe that even Gen 5, I tried to measure it and I could not find why Gen 5 cannot capture the exact context switch overhead, which I was able to measure in the real system. That's why the simulation accuracy was much lower. Because other than that, the instructions it simulated is the same as the operating system, right?